for Omdena and Trash Out that we worked on, and it's the project where I met Nisreen actually. And I got to know OpenStreetMap, OSM, very well in that project, and we produced things like this that you can see on the right, showing the locations of illegal dump sites and where they are. We use that to build a predictive classifier. So probably at the end of this tutorial, you will more or less know everything that I know about OSM. And for that reason, actually, I'm curious to know how much experience everyone has. So maybe at the bottom of the Zoom window, hopefully you have a reactions button. Maybe you can give me a thumbs up or something if you have no experience whatsoever with OSM, if you're completely new to this. Okay, quite a few people completely new, that's good. Give me maybe a heart reaction if you have some experience with OSM, but you still call yourself a beginner. A couple of people, okay. A few more people. Great. And finally, give me the laughing, crying face if you are quite experienced with OSM and you say you're not a beginner anymore. And I can't see anyone. Okay, so great. This tutorial should be useful for all of you then. If at any point you have questions, if there's something that's not clear, then please give me a shout. Or if you happen to know something that I don't and you want to share your expertise on this, then equally, please do share. You can just unmute yourself and speak, or you can put something in the chat. And maybe if there are any, maybe Nisreen, I could ask you to keep an eye on the chat for me, and if there's anything I'm missing there.
Absolutely.
Alert me, thank you. Okay, well, this basically is what I hope that you will get out of the tutorial. So I'm going to give you an overview of OSM and what it is, how it can be used, and the way that the data is stored, the data structure that it comes in, and how you can use it for visualization, so building maps, for very basic spatial analysis, and for pathfinding. And I'm hoping that at the end, you will know, basically you'll know enough about OSM to know what you can do with it for this earthquake challenge, but also for any other kind of project that you might want to do now or in the future. And to have some ideas as well for how you can use OSM. And ideally as well, you'll feel confident enough to get started straight away. It's still the morning in California, so you can work with OSM the rest of your Saturday if you want at the end of this. I'm going to be doing some live coding to show you a bit how to use the various functions of the library that goes along with OSM. So I would invite you, if you can, to open up, well, I'll be using a Google Colab notebook, but open up something and follow along. So you'll see here in the top right, there's the instructions for how to import OSM&X. You have a couple of minutes while I talk through the next couple of slides to get that set up. And then if you want to, you can follow along. And by the end of this tutorial, you will have your own code in OSM. So let's begin with what OSM actually is. So it's a map, basically. It's a project for mapping the whole world. It's run by a charitable foundation, the OpenStreetMap Foundation, I think it's called. And it relies on volunteers around the world to use a variety of sources, including satellite imagery, including physically going to these places themselves and reporting back on what they're like, all kinds of information sources you can imagine, to build these maps. And so here you can see a map of where I live, basically, and it's got exactly what you'd expect from a map. It's got the roads and the names of the roads. You can see that there's a pharmacy labeled. You can see that there are recycling points. There's a cafe. So all of this information is stored in the OSM database. And it's a really big collaboration. It's a really big project. It's been going for years and years. And a lot of big companies, Facebook, Amazon, Uber, rely on OpenStreetMap, sometimes in conjunction with other map sources as well. But they rely on this map. And as a result, because they use it, they also contribute to keeping it updated, keeping it accurate, filling in the gaps, which is good. It means that there's a lot of information there. It's also used by humanitarian agencies like the Red Cross. And the thing that's, I guess, particular about OpenStreetMap is that the data is stored topologically as a graph where you have edges, which are streets or segments of streets, and nodes in between them, which are the intersections between the roads. And as we go through this tutorial, you will get very familiar with what these edges and nodes are and how to deal with this topological data structure. And then along with that, there is metadata, which is, for example, the names of roads and pharmacies and a lot of other details about them as well, as we'll see. So it can be used for building maps and visualization, which is exactly what you would expect from a map. You can identify nearby points of interest. So you can say, show me all of the pharmacies nearby this area. You can get statistics like how far away things are, and how close to the center of a city a place is. And you can use it for pathfinding as well, which I imagine in this earthquake challenge is probably what you are most interested in. So we'll see that. As for why you want to use it, there is some obvious pros to it. It's free. It's a charitable effort. It covers the whole world. Is there a question, or is that just background noise? I think it's background noise. Okay. It covers the whole world, so you can access everything through one API. You can write some code based on one location, and then the code will apply to a different location. It's very accurate. When people have tried to quantify this, generally you can assume that it's accurate to within 10 meters. Some of the volunteer contributors go like up and down the roads with GPS trackers to make sure that the path that they trace with the GPS tracker actually corresponds to where the road is supposed to be. So they do make sure that everything is really accurate. It's got loads of information in it. So you have not just roads, we will be talking mostly about roads, but information on land use. So whether the land is like agricultural, whether it's retail, all kinds of buildings, a huge amount of information in the map. And it comes with its own OSMNX library for accessing the API, which is based on Python. And if you know even basic coding, is really, really easy to get started with OpenStreetMap using this library. And that's what we will be using in this tutorial. There are a couple of, maybe they're not cons exactly, but maybe they're more like limitations to OpenStreetMap. One is that, of course, the map can be incomplete or it can be outdated. If you remember that I said that companies like Amazon are some of the big contributors, you can imagine that in some parts of the world, Amazon have a big presence and a big incentive to keep the map updated. In other parts of the world, Amazon just isn't there, so they don't contribute. Even aside from the companies, the individual contributors, I think, are mostly from developed countries as well. So you might find that the maps have less detail or are less accurate in developing countries. Similarly, rural areas where there are just less people to update the maps. Informal settlements like favelas and shanty towns and things like that as well. The map might be less detailed. If you want to check out how good the map is in the area that you are considering, you can go to this website with the GeoFabric tool, and it will show you a map. You can put in a location, a latitude and a longitude, and it will compare different maps from different sources. So OpenStreetMap and, for example, Google Maps. So you can see what elements might be missing in one or the other. And probably in most cases, you will find actually that OpenStreetMap is the most detailed, or at least there won't be one that's significantly better, but it might be worth checking out before you start your project. The other limitation to this is that when you request from the API, basically a map, a graph of the area that you're interested in, there can be a lot of detail there, and it can be very memory intensive to even just to load the graph. So it's really great for single cities, but if you're trying to look at a larger region or even a whole country, then you'll find that it just crashes. It's not going to work for something on that scale, because the graph is just too complex at that point. So you can get around it by, for example, limiting what you request from the API to just the major roads to make the graph smaller, or otherwise you just have to limit it to smaller areas. And so if you want to, for example, for pathfinding, if your graph is getting too big for you to deal with, you might need some algorithmic creativity to get around these limitations. It's something to bear in mind when you're planning how to use OpenStreetMap in your project. So I would invite you to consider these limitations and these benefits as well as we go through. Think about the earthquake challenge that I guess probably most of you, if not all of you, are signed up for. Think about how you might want to use the things that we're going to do, and what problems or obstacles or limitations you might come up against and how to get around them. So what we're going to do first of all is create a map, a visualization. So I've got a notebook here. And if you are coding along, then hopefully you will have successfully installed and imported OSMNX yourself, and we can get going. So first of all, I'm going to choose a city, and the city I'm going to choose is, well, it's more of a town than a city really, one that's nearby me. Something that's great is that you can request just a place in the world and it will give you the map already. And the way to...
Sorry to interrupt. Could you, there's somebody's asking if you could zoom a little bit.
I can zoom in.
That's better, thank you.
Oh, okay, that's too much. Right. I hope that's okay. So we can request just a city by its name. And the way we request the graph is, so OX is the abbreviation for the OSMNX library. And we just say graph from place. Place I want this city I've specified. And it will return a graph, which I'm going to call G. And then you just say from OX, you go plot graph G. I'll run the cell. And you can see it takes a couple of seconds to load the graph, even from a city. If you're doing this yourself, by the way, I recommend you can either use the same city as me, obviously, or if you're choosing your own, then choose a small one because it will be much quicker. And here we go. This is our first map. There are definitely improvements we can make to it, but there you go. You can see, I guess, so all of these circles are the nodes. So those are the intersections between roads, or sometimes it's the end of a road if it leads to a dead end. And all of the lines in between are not exactly entire roads, they're segments of roads between one intersection and another intersection. And we can limit it. So this is all of the roads in SitchS that OpenStreetMap has, but we can limit it if we want to just the main roads. The way we do that is, so I can I'll copy this code, but I will add extra arguments to graph from place. So I'm going to add a custom filter, and we're going to do it like this. So the roads are called highways, and we can specify a highway. I am cheating if you're wondering. I would definitely, coding in front of like 40 people, I would be making so many mistakes. So I'm copying my code from another screen if you're wondering what I'm doing. So from highway, we can request motorway, trunk, primary, like that. So these are the names of highways, and there is a hierarchy of them. So if you go to the OpenStreetMap wiki, I'll give you a link to all of this kind of stuff at the end of the tutorial, but just to kind of show you. So this is the wiki for OpenStreetMap. This is the highways, and it tells you these are the hierarchies of highways. So motorway is obviously the most prominent roads in a country, and it goes down to other kinds of roads as well. So we can just request the main roads and then run the cell. And here you can see that this is a much smaller graph. So we've only got the main roads here. Similarly, I'm just going to copy this again. And we can request, instead of the main roads, we can do the opposite, and we can just ask for residential.
Hi, Emma. Sorry to interrupt. Actually, the entities that you listed down with the pipeline symbols, are those subcategories under the supercategory of highway?
Yes. So every highway is given, I mean, every country probably has a different way of classifying what their roads are. So OSM has developed its own taxonomy, its own classification. And yeah, so these are all different types of roads. So every highway will have a type, like residential or whatever else. So here, now we have a different map, which is a completely different shape because it's only one part of the city that has residential streets in it. There we go. So as well as requesting a graph by the name of the place, we can also request a map from coordinates. So I've just specified these are the latitude and longitude that actually correspond to the same city in my case. So we can do, instead of graph from place, we're now going to do graph from point. And we need a tuple of the latitude and the longitude. And then we say the distance is another argument. I think by default it's 1 kilometer, but we're going to go a bit smaller. This is the distance in meters that we want. And then, of course, we go plot. Run this, and we should have a map of the same place, but smaller, because it's only going to be 500 meters in every direction. No, I forgot to call this G. There we go. So this is a map of the area around a particular latitude and longitude. Now, this is quite ugly. You would probably agree, as a map. So there are certain things we can do to improve the aesthetics. So I'm just going to copy this graph line, but I'm going to add some extra arguments. So let's make the background color white. And the edge color, so that's the color of the roads. Let's make that black. And the nodes themselves, they are not very intuitive when you're looking at a map. It's useful to see for understanding OpenStreetMap, but if you just want to see what the city looks like, they're not very good. So let's make the node size 0. And then there, that is looking much better, much nicer map. Okay, so we've done some basic visualization now. I'm going to go back to the slide. So hopefully you've seen from this that in OpenStreetMap, the roads are represented mostly as edges of a graph that are connected by nodes, and the nodes represent intersections and dead ends, and the edges are the segments of the road in between those nodes. The roads are also stored with metadata. Actually, I didn't show you this. So let's move on a little bit, actually. Right, so we have G, which is our graph. We're going to convert it to a geodata frame now. So the way we're going to do that is graph to geodata frames. And a geodata frame is a thing that comes from GeoPandas. And if you're familiar with the Pandas library in Python, it's very similar, but it's more specialized to geospatial kinds of data. So this will give us two geodata frames for the nodes and the edges. And then let's have a look at the edges, which has been our graphs. Okay, so here, every row here is a segment of a road. They are indexed by U and V, which are actually correspond to the nodes. So every segment of a road has to start somewhere and end somewhere. So U and V are where it starts and ends. Sometimes you might have parallel roads, so they start at the same node and they end at the same node. And then if those edges exist, then they'll have different keys, but in most cases, the key is just 0.
Emma, I have a question.
Yeah.
The nodes, what are nodes? Are they like little points where two streets meet together, two different streets meet together, or?
Yeah, exactly. That's exactly it. It's the intersection between two roads.
Okay.
So we also have other attributes or other characteristics about these roads. So one is whether they are one way or not, which is binary, true or false. The other one is the name of the road. Sometimes they don't have a name, which I think is maybe because they're part of, oh no, I know why it is in that case actually. I'll show you in a moment. I'm going to zoom out just because I can't scroll properly.
Hi, Emma. Can you please repeat the U and V again?
Yes, so every row in this geodata frame is an edge, and an edge is a segment of a road. And because of what a graph is edges which are joined by nodes. So in our case, these are segments of roads which are connected by intersections. The edge, by definition, has to start at a node and end at a node. And so U and V are the start and the end of the edge. In other words, they are the nodes. You can see every road as well has an ID, just specific to OSM. So these numbers here are the OSM IDs for the nodes where the segment of a road begins and ends. Does that make sense?
Yes, and is it in terms of longitudes and latitudes?
That's, I will show you that later. It's you can also get the latitude and longitude of these nodes, but this is just a reference that's specific to OSM.
There was also a question about the key, that would these keys be unique across the world?
The key is only unique if you have two edges that have the same U and the same V. So you might have two parallel roads. They start in the same place and they end in the same place, but they're different roads. So you can't separate them by the U and the V because it's the same. When that happens, one of them will have a key of 0 and one of them will have a key of 1. But most roads in the world are unique in the sense that they start and end in a unique place. So in most cases, the key is just 0. I hope that answers the question.
Does those roads should necessarily be parallel? I mean, they will have the same key if they start at the same node and end at the same node, right? No matter how complex those roads are, I mean, only the start and end nodes matter, right? For the key to be unique or same.
Yes, that's true. Yes, they don't necessarily have to be parallel. They just have to start and end in the same place.
Sorry, I have one more question.
Yes.
I just wanted to know how the OSM IDs are related to U and V.
So the column for OSM ID, so every node and every edge in OSM has to have its own ID. Beyond that, I don't know how they're created. I don't know if there's any like ordering to the numbers. This is really pushing the limits of my knowledge of OSM. But if you have an edge in mind, you can access the nodes that correspond to it by the U and V. And if you have a node, you can also get the edges that are attached to the node the other way around, which is basically any kind of topological analysis that you want to do on the graph. You need to know which edges are attached to which nodes in order to compute, anything. So this is why it's important to have them kind of corresponding to each other in a geodata frame.
So the OSM ID will represent an ID for the edge.
Yes, this is for an edge.
Mm-hmm. Okay. And if there are multiple edges, then like is the representation per row for a particular edge, or there can be multiple edges because you're saying that this is a segment of a road? And I mean, I don't know how this distribution works, honestly, so that's why I'm asking.
Okay. So, okay, let me do something else. So, lost myself now. Okay, so for every row, which is an edge, it has an ID as well as the ID of the beginning and the end, which are the nodes. It also has a geometry, which is maybe more intuitive if you're thinking about a road. It comes in this format of line string, which you don't have to worry about, but it's a sequence of points. And you can see here the 1 point something and the 41 point something are the latitude and longitude. So maybe let's just plot what they look like. So if we go to edges, if we just take the first one, so I'm indexing from the data frame, the geodata frame edges. I'm getting the column called geometry, and I'm just requesting the first one. So this gives you the actual geometry of the road. This is not the entire road, this is a segment, which means up here, there will be some kind of intersection with another road. Down here, there'll be another intersection with another road. And the other way we can look at it is just, if we print it, then we'll get this in text. So you have, this is a latitude and longitude, and this is another latitude and longitude, and this is another latitude and longitude. And all of these points together form the line. So that's what the segment of a road is. So that was for the first row, this one. And we can see that the type of highway is called a secondary link. The name of the road is this. And by definition, it has to have a node at the beginning and a node at the end, because that's what an edge is in a graph. So the node at the beginning is U and the node at the end is V.
Emma, do you have an idea about the granularity? You said these are all latitudes and longitudes. So what are these segments of meters, or how?
Well, so this is the length. So this tells you how long the segment is in meters, actually. They're not defined by, the segment is only defined by wherever there's an intersection, you have to put a node. Wherever the road ends, you have to put a node. And between two nodes, that's an edge, which is just, in like mathematics or computer science, this is the definition of a graph. Wherever you have an edge between two nodes, it's an edge. And so this is how OpenStreetMap represents the roads themselves. So you can have a really long road, wherever it crosses other roads, wherever there are intersections, you put nodes, and then you have to divide up the road into these segments.
Oh, okay. Because there were a bunch of latitudes and longitudes when you showed the edges, right? Of the geometry,
Yeah.
this thing. So those latitudes and longitudes, they correspond to, like I understand the full length maybe was 193.542, but then each breakup is a part of this 193, and I was asking for what is the granularity.
I see. I don't know the answer to that question.
Okay, no problem. I mean, there's lots we have to look up. I think there's a lot of information in all this. So, yeah.
Okay. So you have the geometry of the road, which is this line string, and you also have certain other attributes. So you have the name of it, you have the length, you have, in some cases, how many lanes it has. This one doesn't have a name because the road is called C31. And sometimes you also have the speed limit. So this is 80 kilometers per hour is the legal speed limit on this road, and certain other information as well, like if it's a bridge and things like that. So this means that you can treat the roads in two ways. You can look at their geometry in order to plot them, or you can look at it just as a kind of simple tabular database of here is a road with a name and a length and whether it's one way or not. So these are two different ways of looking at the roads. Depending on what you want to do with OpenStreetMap, these attributes can be used in different ways. So this is hopefully what you've maybe understood. I think any confusion about the nodes and the edges, it might get easier as we go further through and I show you more examples of how to use things. But the roads are represented as edges of the graph, which are connected by nodes. The nodes are intersections and dead ends. And the roads are also stored along with the metadata, which includes the name and their speed limit and things like this. And as well as these details, which are basically text-based or numerical, they also come with a geometry which allows you to plot things and later on to do more advanced things. This is a summary of what I hope you've taken away so far.
Emma, when you say road comes with geometry, what does that mean? I know you explained it, but I'm still not very clear what that means. Is it like the shape of the road, like a square, box, semi, or circle or something? What does that mean? Road comes with the geometry.
Yes, you've got the right idea. They're not defined by how wide they are. So they're not polygons in the sense of plotting a rectangle where one dimension is the length of the road and the other dimension is the width. It's not a geometry in that sense. It's a geometry in the sense that it's a line string. So it's just a series of points, which is in 2 dimensions because each point has a latitude and a longitude. So you can plot it, but it doesn't give you the width of the road. It just gives you the shape.
Okay, thank you.
So, so can we think of it as the series of kind of a coordinate that shapes the edges?
Yes, they're the coordinates that shape the edges.
Okay.
Yes. So you can imagine that if you want to plot the graph, then knowing the geometry is really important. If you want to know the distance from one thing to another thing, then the geometry is really important. If you wanted to just know, for example, what is the average length of roads in this city, you actually don't need the geometry. All you need is this kind of information. So you just need the metadata for that. If you want to know how many residential roads there are, then all you need to do is index this highway column. So these are why the metadata and the geometry are kind of 2 different ways of getting information about the roads, depending on what you want to do with it.
So the length of, for example, the U3, the first road, 193.52, is actually the miles from one node to the other, or kilometers, or is that what that means over there?
It's meters from one node to another.
Okay, all right.
Yeah.
Thank you.
So what we're going to go on to next is a bit more about what to do with graphs and polygons. So
hey, Emma, I have a question. This is Mahesh.
yeah.
So how this is used in the current project, like where this is exactly being used?
So I am going to show you what you can do with, I think pathfinding is probably the most important. So you have a graph and you define a node A and a node B, and you want to find the path in between them, and then the fastest road, or the road that avoids, the path that avoids small roads, for example, because maybe small roads are more dangerous, something like that. So I will show you that. What's the next thing I wanted to do? So, no problem. I think going back to the visualization actually might help a bit more. So let's have a look then at this column of highway, which tells you the types of highway. So again, we're going for the edges, geodata frame, geometry, and we can get the value counts. So highway, that's what I wanted. Not sure. So ignore the error, but these are all the different types of highways. So every segment of a road has been categorized as, for example, residential, pedestrian, and so on. And this is the number of different segments that you have for each type. And we can use this actually to improve the map that we plotted earlier. So this is what I've done. So this is making every type of road a different edge color, more or less. So for every E, so every edge in this column of highways, if E contains the word secondary, we make it this color, so quite dark. If E contains the word tertiary, we make it a bit lighter. If it contains residential, we make it a bit lighter. Similarly, for line width, again, I'm indexing the highway column, and I'll make the width of the line 5 if this edge contains secondary or tertiary. I'll make it 3 if it's residential, otherwise I'll make it 1. So this is the function we used before, plot graph. And now instead of giving all of the edges the same color, the edge color is going to be what I defined here. The line width is going to be what I defined here. And we'll set the node size to 0 because it looks nicer. And you can see that being able to categorize the roads by different types means that you can do something that's a bit more interesting. So this graph is better in the sense that you can see where the main roads are much more easily, this dark, thick one. And you can see the minor roads, which are paler and thinner. So you can, the way you plot graphs can be quite flexible depending on the needs that you want. And as another example of what further needs you might have, so this is almost the same, except I'm now going to make footways or pedestrian highways. So these are places that obviously are not accessible by cars or anything else. They are pedestrianized. I'm going to make these blue. And steps was another type of highway that we had. So if it includes steps, I'm going to make it red. And this might be useful because, again, steps means that you can't drive along it. It's also not accessible for people with mobility problems. Depending on your purposes, this might be quite useful. And so this is a really easy way to visualize important information. You can get the edges that have some kind of meaning relevant to your purpose, and you can plot them accordingly. Does this help you to understand what edges are as well? Because you can see here, for example, so this blue one, this is a pedestrian road because we've said if it is pedestrian or if it's footway, then make it blue. And so the edge is defined as a starting point. So this is a node, although we've made the node size 0, so we can't see it, but we know that there is a node here. And we know that there is a node at the other end. And so the path in between them is called an edge. So that is the edge. I'm looking for an example of whether you can see a separate road segment, but, oh yeah, we can actually. So there's a road that starts here at this roundabout, and it goes round to this road here. I'm going to zoom in a bit actually because it might be difficult to see. So this road here, this is one road. So it has a node at the beginning at this roundabout. It has a node at the end at this intersection. But there's another road in the middle which kind of cuts this in half. So there will be a node in the middle as well. And we can even see that because they're different widths, they're different colors as well, it means that they've been assigned a different road type. So you can see even more clearly that these are, even though it's the same road, they're two different segments. And because they're separated by a node here, it means that they appear in the graph as two separate edges. And that makes sense if you think about the fact that the graph, basically the point of having a graph like this is to plot, to find routes. You can imagine that if you're starting at this roundabout and you go along here, at this point you have a choice to make. You can turn right and go down the blue road, or you can continue along the same road. And so that's why you need to have a node here, and that's why you need to treat these as separate edges of the graph.
I have a question here actually. Will all those, will all those edges between all those nodes be counted as separate roads, or the main route, the whole beginning from the first node and ending at the last node, excluding the separator in the middle, will be counted as a road?
Yes, so the way you access the information is not by road, it's by edge, which is a segment of a road.
So all of the segments will be counted as separate routes, right?
Yes. So they'll be, they have separate IDs, they have separate rows in a geodata frame. Yes, they're separate. If you really need to know which edges correspond to the same road, you could use the name, because the name obviously is just text that's attached to the edge. And so these two edges, if they're part of the same road, in real life they'll have the same name, which means in the geodata frame, which we saw here, look, you can see here, in fact. So these two rows start at the same node, but they end at different nodes because they have a different V value. And they have the same name. They're both called collaborators de los postes, which means that the start of the road is maybe this one, and the end of the road is maybe this one. But they meet in the middle because, of course, they're actually the same road. So they have this is the node where they meet. And if you really needed to know which road, you could index it by the name.
If it's possible, can you share with us the notebook again? Thank you.
Yes, definitely. I'll share, well, I think Nisreen already has the slides. I'll share the notebook as well, so Nisreen can distribute it. And also you can contact me directly in case you don't receive it for any reason.
Thank you so much.
Yeah, I'll share it as a resource and I'll put it on the Google Drive. Thank you.
Okay, right. So, where we go next? So rows as geometries. So we've seen that the road, or the edge, which is a segment of a road, is defined by these points, which are latitudes and longitudes, and you can visualize it as a line string. And the reason why this is useful is that we can find the distance between places, for example. So, in fact, I will also show you as well what the node's geodata frame looks like. There's less information because if you think about what it is in real life, an edge is important because an edge is a road and it actually has attributes like a speed limit. A node it's just an intersection. It doesn't really, there's nothing really to say about it. So you have the OSM ID, which is the ID of the node. You have the X and Y, which is the latitude and longitude, and you have the street count, which is how many roads are coming off this node. And then, of course, you have the geometry. The geometry is not a line string, so the geometry of an edge is a line string because it has to be a line because it's a road, it's an edge. The geometry of a node is just a point. I hope that's intuitive. So we can find the distance from any point that you have in mind to a road. If you want to know, for example, if, I don't know, someone is stranded or there's some kind of damage from the earthquake or something, and you want to know, is it easily accessible by a road or is it really far away and an emergency vehicle wouldn't be able to get there, something like that. So the way we can do this is, so to get this point is, this library is based on several other libraries, one of which is Shapely. So I'm actually going to import another library here, which allows us to declare points, which is a certain data type. And let's say there is a person who is stranded or something like that. So the place where they are is, we're going to say it's the latitude and longitude that I already used earlier, which I know is a point in Sitges, in the city that I'm interested in. And we can calculate the distance from this point, I am here, to every road in the graph. So we can iterate through the edges of the graph like this. And if we iterate through, it will give us the index, which we don't need, and the road segment. And let's just, this will end up being quite ugly, but let's just print out. So we'll have, of the road segment, we'll have a name of the road from the data frame, which is up here. So it'll have a name. Yeah. And the way to get the distance is really easy. So we have, if we go use the geometry, which we know is a line string, all we have to do is say distance to the point which we're defining here, which is I am here. So for every edge, it will print out the name of the road. So sometimes the name will be repeated because we know that the edges, a road can sometimes have more than one edge. And we're going through the edges so that they might have the same name. And all we're doing is saying from this geometry, get the distance to I am here. We run this. Oh, what have I done? So I missed a space. Right. Okay, so we can see this. So the distance from this road, there are two edges to this road, and the distance from this point I am here has, of course, two different distances. There's a trick to this, which is really important, which is when you get the distance, by default, it's in degrees. It's not in miles or meters or anything that would make sense to you intuitively. It's in degrees. So if we want to find, for example, which is the closest road to where I am and what is the distance, we need to do something else, which is, so for a start, we can, instead of printing, let's save them all to a list. So we'll make a list of road names and we'll make a list of road distances. And what we will do is, instead of printing, we're going to append to this list road names. I'm going to append the name of the road segment. And we will calculate the distance as we did before. So we know that that's road seg geometry. I am here. And we append that to road distances. And then what we can do is once we've stored the names and the distances, we can just get the index of the minimum. So out of row distances, we will get the index of the minimum. So then we can print, so then we can print closest road is called. And then we index road names by this index that we just made. And then we can print distance from specified point meters is, so it would be the road distances, which we index by the index that we want. But what's important is that to convert from degrees into meters, you need to know the radius of the Earth in meters, which I will just tell you now is this number. So if you multiply by that number, then you convert the degrees to meters. And there we go. So that's it. We've got the minimum of all of the road distances, and the closest road is this one. And the point that we specified in latitude and longitude is 20.9 meters away from this road.
So Emma, I had a question here. So when it's looking at the distances, right, from I am here to all the different roads that are around it, is it also looking at the minimum distance between each of the roads?
Sorry, each of the rows in the data frame.
So no, not roads. So you have one point, right? And around it, there are like 5 or 10 roads or whatever, highways or whatever. So it's looking at that point, I'm here, and then calculating the distance to each of the roads. And then what you have printed is a minimum of all the distances from the different roads. So for each of the road, is it also looking at a minimum?
Yes, it's also looking at, it's the minimum distance between the point and the road.
Okay.
Yes.
Emma, another question continuing on with Nishrin's question is, so we found that the closest road is Carrer de la Veste, right?
Mm-hmm.
Can we have an option of having maybe another close road next to Carrer de la Veste in case, this road is completely, with earthquake and stuff like it's gone, it's not a way to walk through there. Is there an alternate road? Is there a possibility to do that too?
Yes, so if you know that this road is just destroyed, you can delete it from the graph. You can just, so the best way to do that is if you turn the graph into a geodata frame, and then you just delete the row, and then you convert the geodata frame back into a graph, then you have a graph that's missing that road. And you can say, find the closest road of the graph, which is missing certain roads.
Okay, so the maps that we get, say that, for example, when you have an earthquake, we have a map with the latest information where the earthquake happened, and we know some of these roads are destroyed and there are some roads open. So we would get the latest, greatest map that gives us the latest information after the earthquake, correct? And that is always going to be there, correct?
Yes.
Okay.
Okay, I'm going to show you polygons now, and then I will come back to your question about how to select or how to deselect roads that shouldn't be used.
Actually, I have a question regarding the
Yeah.
degrees that you showed. The degrees are calculated in terms of what actually? I mean, I didn't get that part or missed something.
So these are degrees of the Earth, because the Earth is a sphere, so it can be measured in degrees, which for some purposes is better than trying to measure it as a Euclidean distance, because the surface of the Earth isn't flat. That's the only reason. Okay. Right. polygons. So we've seen points, which is just the latitude and longitude. We've seen, and if you join several points together, you get a line string, which is a line, but in 2 dimensions. If you join lines together, then you get polygons. So I'm going to show you now about polygons, and then there will be something interesting to say about how you can define a part of the city which has been destroyed by an earthquake, for example. So another great thing about this OSMNX library is that you can get what are called geometries from, and you can get it from any of these things, from an address, from a place. I'm going to go from a point, the same latitude and longitude that I used before. And you can get geometries according to how they're tagged. So for this, I'm going to say building. So any geometry which is a building, so where building is true, return the geometry. I'm going to specify distance from my point of 200 meters. And this will return a geodata frame called buildings. And then let's look at the buildings geodata frame. Okay, so this is another geodata frame. These are all the buildings that are close. They also have an OSM ID. They have nodes as well, which correspond to not intersections between roads or road segments in this case, but they are the edges of a polygon. So you have certain things like the metadata about this one, for example, is a supermarket called Carrefour. And it's got the geometry that it has is a polygon. And you can see again, you've got 1.8 something, 41.2 something. So this is roughly the same latitude and longitude format that we had before for line string, but now it's a polygon. So we can plot it. In fact, if we go, so geometry column of buildings, and we get the first row. Then we can see this is the outline, the footprint of this supermarket. So if we want to plot it, then very simply, so I'll show you again. So we've done this before, but just to repeat, to re-emphasize, we can get 2 geodata frames for nodes and edges by turning the graph that we had into, no, actually I'm gonna, because this was only 200 meters, I'm gonna create a new graph which is smaller. So we go graph from points, equal of the latitude and longitude, the distance is 200, and then we convert this graph to a geodata frame. And then we're gonna plot the edges onto an axis. So we've got edges, got plots, and let's just say the line width is 1, and the edge color is typo. And let's plot the buildings. So again, from this data frame, geodata frame, you can just use this command plot onto an axis. So this is the axis that we've got here. And for the face color of the buildings, we are going to do something. So the color, let's say it is blue if shops, so shops, go a bit further over, there are several other categories. Yeah, shop, okay, so if shop equals supermarket, then plot it in blue. Otherwise, if it's not, then just make it dark. For the shop column in for every shop, in fact, in the shop group. So then we say that the face color that we're plotting should be this. Okay, so we've with this line we've plotted the edges, which is the map, the roads. So every edge is a road segment, as we know. These are in grey, and then we've also plotted all of the buildings. And using this kind of logic, you can see that there's one polygon which is in blue, which means of all of the buildings in this geodata frame, only one of them was a supermarket, and it was this one. And all of the other buildings are there, but plotted in grey. So this is a good way of visualizing different types of buildings that you might have. So the other thing you can do with that is, this is a really silly example, which is given that we have a point which we can define, and we have a polygon, which is the polygon of this building, we can just say, so if we go buildings, geometry, and we'll get the first one, which is the supermarket, and we can just say contains I am here, which is the point that we had, and it will return true or false. So the point that we defined is not physically in the supermarket. So this person who's asking for help and says I am here is not in the supermarket. It's a bit of a contrived example, but you can imagine that if you define a polygon yourself, and it could be much bigger than a building, it could be an entire region that's been devastated by an earthquake, and you have a lot of points which can be where people are, but also remember that these nodes of the graph, where there are intersections of roads, these are also points, and you can also use basically this function. You can just take any polygon, this is a polygon, define the polygon how you want, and you just do dot contains the point that you're interested in. And any that's true, so any nodes that appear in your polygon, you can say these are dangerous. And then if you know the nodes, if we go back up to where we had the geodata frame for the edges, which is this one, if you know, for example, that the node which is indexed by this number is in your danger zone, then you can drop this whole row because you know that, that this is dangerous. Similarly, because the geometry is defined by latitudes and longitudes, this is the line string for this segment of road. It's composed of a series of latitudes and longitudes. So you can say for every point in this line string, if that's within your polygon of disaster zone, then flag that as true, and you can delete this whole row of this geodata frame. And then if you turn the geodata frame back into a graph, which is, remember, we turned the graph into a geodata frame by doing this, just swap around graph and GDFS and you have the reverse function. Once you've deleted the row, you can convert it back into a graph. And you can then find a new route.
Emma, I have a question actually. Are all those buildings, I mean, the whole region of the building, is it considered as a single node?
No, they are not considered a single node. So every, so where did our building go? So if we get again, the first building, which was the supermarket. So it's defined as a polygon. A polygon also, if you actually wanted to physically, plot this on a map, basically what you would need to know is the latitude and longitude of all of the corners, and then you just draw a line between all of the corners, right? So it's the same thing. If we print it out as text, then what we have is the polygon is defined by all of the corners, which are these latitudes and longitudes. So each of these in this case, it's not a node, but if you want to treat it as a node, you can to make a graph out of that if you wanted to, or you just say for this latitude and longitude, you turn it into a point, which you just do like this. This is a point, and then you can say, in fact, let's do that. So, buildings, geometry, first row, and we say, does it contain the points? False, I think, because it's on the edge and maybe there's a rounding error. But you can see that you can, it's flexible enough that you can take these geometries like line strings and polygons. You can take the points from them, you can turn them into nodes. You can use them to find distances between them. You can use them to find if one intersects with the other, so if the point is inside a polygon. And it's quite flexible like that, depending on what the question is that you want to answer.
I just want to give a reminder here that we have 13 minutes. So, you know, Emma, if you have anything to cover, you can use that time.
Okay, I will try and speed up then. So we've seen that you can handle the roads and also other things like buildings as graphs or as polygons. And if you treat them as, well, polygons or more generally geometries, which includes points and line strings, this allows you to find intersections. So whether a point is in a polygon, for example, or whether two polygons overlap. The closest distance between two geometries, so the closest distance between a road and a point that you specified, for example. Graphs, on the other hand, allow you to find routes. So let's try and cover this quite quickly. So we've got the graph from the city that we specified. I've chosen 2 points of interest called A and B, which are just latitudes and longitudes that I know are in the city. So first of all, we're going to find the nearest graph node. So supposing we're trying to navigate the city by roads, so we need to know where is the closest point on the map, closest point on the road for each of these points. So there is a function for that from OSM, which is distance dot nearest nodes. And you need to specify the graph, which is G. And the latitude and longitude, so the A0 and A1. So the 2 parts of this point, the latitude and longitude. And we'll call this the A node. And we'll do the same for B. To find the shortest path between them, again, a very simple function for this. So distance dot shortest path. We need to specify the graph as well, again, that we're going to use. We specify the origin, so where we're starting from, which is A node, and where we're ending up, the destination, which is B node. And then we will plot the shortest path. So we already know how to plot things. But this time we're going to plot the route as well. So again, we need the graph, which is the map, the path. So once we've got the shortest path, so we need the shortest path, and just a few other things to make it look nice. So the width of the route that we're plotting. We don't want to visualize the nodes because it makes it basically look ugly, and we'll make the background color white. So if we run this, there we go. So we have this graph in grey, the map, is all of the roads of the city, which we've already seen before. And now it's calculated the shortest distance from point A, which was, I forget which way around it is, but one of these is point A and one of these is point B. More specifically, it's the A node, which is the nearest node on the graph to the point, and it's found the shortest route, and you can plot it like this. One thing to be careful of is that this is taking into account all of the graph, and we saw before that some of them are pedestrian streets, some of them are steps, things like that. So there are certain other things that you might want to take into account, like for the graph, you might want to specify that it should only return the roads which are drivable. So the way you do that is you can say network type equals drive. Another thing is the shortest path by default is just the shortest path by the length. But of course, different roads have different speed limits associated with them. So you might actually want to define the shortest path by the travel time between them, which takes into account the speed limits and not just the distance in meters or miles. And if we do this, because this is not an argument of the crossing function, this is an argument of the shortest path. So this is a different route. This one used the roads going along here, but if we specify drivable roads and ones that are fastest, it actually takes us up here. So it's a different route. So you can calculate different routes according to different things. Another thing, which in the interest of time, I'm not going to go into, but you can specify that. So the edges obviously have a length because it's specified, and because of the geometry, you can easily calculate the length, and so that's given to you when you get the graph from the API. They also have a speed limit, which is either specified or it's inferred by the function. But you can also apply your own weighting. So instead of saying, give me the shortest route, which minimizes the length, instead of saying, give me the quickest route, which minimizes the time taken based on distance and speed, you can also assign for each edge, for example, how dangerous it is, maybe. And you can request the route that is shortest, not by time or by distance, but minimizing how dangerous it is. So this could be an alternative to defining roads that you don't want at all. You can remove those edges, but also you could just give them a high weight for how dangerous they are and then try to minimize that. So I won't show you that. I won't show you these. Just one other thing that might be useful for you one day is the other type of polygon you can have is land use. I'm just going to copy and paste this rather than typing. So the other kind of geometry you can have, we saw buildings already. We can also get land use, and you get all kinds of types of land, including if it's used for retail, if it's used for residential, if it's used for even forest and farmland and stuff, which I'll show you here. So this is another geodata frame that shows, again, you have a lot of polygons, and these polygons tell you, so this is a swimming pool, this is a vineyard, all these kinds of things. So forest, there are a lot of polygons corresponding to forest in this area, grass, residential. And again, you can plot these if you want. So so in this case, I'm selecting from the graph anything that's used as forest. I'm going to call it forest, and then I can plot it by.
Oh, can you please repeat what's the land use here?
Sorry.
I didn't get that part. What you refer to by land use.
Land use. So it's, well, these are examples. So they're polygons. Whenever someone has determined that this part of the land is forest land, then there's been a polygon. So you determine the outline. So the corners of this patch of land, which define the polygon. So the shape that it takes up in real life, and then it's uploaded to the OSM database with the tag forest, and you say this is what the land is used for, it is a forest. These are alternative things that land is used for, so grass, residential, vineyard, railway. These are all things where someone has determined this patch of land is a railway, part of a railway, and in the database, they come up as polygons, so you can plot them. And again, the reason why you would want polygons is maybe because you can plot them. So this is the city. So we haven't plotted the roads this time, but we've plotted different items. So dim gray color is residential. So this is like over here is residential and down here is residential. Dark green is forest, and you can see where all of the forest patches are. So you might want to use this. I mean, maybe a forest is a safer place to be than a residential area. So you can use these polygons to determine safety. Maybe if you have a node of a graph, or if you have a point, latitude and longitude that you determine yourself, you can determine if they are inside these polygons or not, and do something useful with that. So that's where I'll stop, I think. So we've looked at this, we've looked at pathfinding, and as I said, you should consider what road types. So are you looking for drivable roads? Are you looking for walkable roads? What attribute do you want to optimize for? Do you want to optimize for distance or time? And for more advanced things, you can avoid a road or an intersection that's dangerous or that's destroyed in an earthquake by dropping the edge or dropping the node. You can create custom attributes as well. So if you define an edge as being dangerous and you give it some kind of measure of how dangerous it is, you can optimize for avoiding those kinds of areas. Bear in mind, as I said at the beginning, if you have really large graphs, so large cities, for example, any of these kind of algorithms will take a really long time and might even just crash. So if you're looking at large areas, you might need to be a bit more creative with your pathfinding algorithms. Also, if you're trying to do anything brute force, so if you have like 1,000 origins and you're trying to get to one destination and you try and do this through brute force, you'll also come into problems. So this is where you'll need creativity.
Actually, I had another question. Actually, what are those values? I mean, corresponding to the landmark names. I mean, are those the areas of the polygons, or those are actually IDs to mark those polygons?
These polygons.
Yeah, these values. I mean, can you go a bit down?
A bit down.
Yeah, here. I mean, the values beside
these numbers.
The names. Yeah.
Sorry, I went through this really quickly and I didn't explain. This is just going through the geodata frame that I created above, and it's just asking for all of the individual types of land use and how often they occur. So there are 108 polygons which are labeled as forest. That's all it means.
Hi, Emma. Can I ask you one more question?
Emma, I'd let Emma finish before we can ask, because we're running out of time. So
sure.
I'd let her finish whatever she needs to.
All right. Sorry, I'm having to rush to the last bit. The last bit is probably the most interesting.
No
as well.
problem, Emma. I think we can take a few more minutes. I just want to be aware of people wanting to leave and so on. So
yes.
But yeah, please go ahead and take a few minutes.
Okay. Right, so pathfinding is probably the most interesting, but the land use is another probably quite interesting thing to look at. So you can have polygons that are available for residential, forest, water as well, all kinds of things. So I've put a list of further resources which shows more examples like the ones I've shown you with in a notebook with documentation with descriptions. Also, there's the documentation, there's the wiki, there's a whole online course which is quite good for GIS which is, I think it's geographical information systems. And it includes how to use OSM. If you are really interested in OSM itself, there's an academic paper. As I said, Nisreen has these slides and we'll distribute them so you can have these links yourself. I'll also share the notebook as well. If you have any other questions, if you need to leave now, but you have questions later, just send me an email. This is my email address, and I'll be happy to answer questions if I can.
Thank you so much, Emma. This was incredibly useful, and I think it'll be of great use to this team.